All right, we're going to take a look at identifying rational zeros for a polynomial function. This is going to follow the notes in Glendon 7.6. It's important to recognize that in this particular section, we're looking for possible rational zeros, and the key word here is they're possible and they're rational. This theorem does not identify actual zeros until you've actually proven that they are ones, and it's not going to identify irrational zeros. So the key thought on this one is identifying your p's over your q's, okay? P's are going to be factors of your constant term over here, and q's are going to be factors of your leading term over here, okay? So 9, the possible factors of 9, we have 1 and 9, and then we have 3 times 3. Those are the only 3 that we have. And for 2, our possible values for q are the factors of 1 and 2. And so now I need to pair them all together here, okay? So the other key thing is they could all be positive or negative just because of the many ways of producing positive numbers, be it a positive times a positive or a negative times a negative, okay? So first off, we're going to put the 1 and we're going to place him over the 1. And then next we're going to take that 1 and we're going to place him over the 2, okay? So those are so far 2 of our possible rational roots. In cases like this, we just leave 1s over 1s, or you could just write a 1, okay? Now we keep going. Now we're going to have a 3, and we're going to place him over the 1. And then we're going to take our 3, and we're also going to place him over our 2, okay? Lastly, we're going to deal with our 9. So we're going to first deal with the fact that we have a 9 over a 1. And then lastly, we're going to deal with the fact that we have a 9, and we're going to place him over the 2. This entire list right here are all the possible rational roots for our first polynomial function. All right, moving right along here, let's look at part B where we're given this other polynomial function. This is the scenario where we love the fact that our leading coefficient's 1 because our q, the only way to get a q of 1 is just having a q of 1. It's the only factor. It's 105 that we really need to worry about. The possible factors for 105, they start all the way at 1 and go up to 105. 1 times 105. Next, we have a 3, and he gets multiplied by a 35. Next, we have a 5, and he gets multiplied by a 21. And then the next one we have are 7 and 15, okay? So now we need to place each of those over 1, or we could just simply write a plus or minus in each of these because it's going to be a positive or a negative version of any of these possibilities here, okay? Remember, just being divided by 1 is really just going to produce itself. All right, 2 more examples. Here we're given a real-world problem where it really is going to require that we interpret what the question is saying. It's giving us a volume of a rectangle. Once again, volume is just going to be length times width times height, okay? And so we're also given dimensions here that the width of this is 4 centimeters less than the height. So let's let the height be x, okay? Then the width, if it's 4 centimeters less, is going to be x minus 4. And the length is 6 centimeters more, so it's going to be x plus 6. So here is our polynomial, okay? And here it is going to be set equal to 675. Now we're really going to be looking for a value for x that's going to satisfy this equation. But one of the suggestive things to do is to get it set equal to 0, then solve for x. Then we're really just going to be looking for solving, okay? So let's FOIL it on out. X plus 6 times x minus 4, that's so far going to give me x squared. We're going to get a negative 4x. We're going to get a positive 6x and a negative 24. Now we're going to have to take this quantity and multiply it by an x. We'll still deal with that 675 business in a second here. These two are going to be like terms, and then we're going to distribute the x in here, okay, giving me an x to the third. Negative 4x plus 6x, that's 2x, times the x is going to give me 2x squared. Then we're going to have a negative 24x, and then I'm just going to skip ahead here, and I'm going to subtract 675. So now my equation is equal to 0, so I'm looking for values of x that will make this equal to 0, aka my solutions, okay? So here's where I want you to take a step back, figure out what your possible p's over your q's are, okay? So I want you on your own, identify the p's over the q's. Then you're going to make a little table. It's going to help us hone in on a little bit. You can even use Descartes' rule of signs to recognize that there's only going to be one positive real zero. Look, there's only going to be one sign change. Therefore, there has to be one positive. And if you take a look at your possibilities in your table, you're going to learn that 9 is actually going to be a solution. So if we actually plug that into our little expression to find the volume, okay, we're going to have 9 plus 6 times the quantity of 9 minus 4 times 9. So we have 15 times 5 times 9, and ta-da, it equals the volume. So yeah, I skipped a few steps, so please make sure you're checking over your P's over your Q's with the process done in the textbook. So now let's take a look at example 3. All right, so looking at our last example here, example 3, notice that the textbook once again has you have a starting spot of identifying your P's over your Q's. So I'd like for you to start there, identifying your P's and your Q's, and plugging in these possibilities, focusing in on those possibilities on your XY table. So make sure you pause me, and then you can listen to the last couple steps. So when you look at your XY table, after honing in on your possibilities, you'll probably see that 5 has a Y value of 0. So now we can plug that into synthetic division because that's going to help us break down this polynomial even more. Okay, so I'm going to plug that in here to my synthetic division. And then we're going to pull down the 2. We're going to multiply. We're going to add. We're going to multiply and add. And multiply and add, and ta-da, we verified it, what we've seen on our graphing calculator or on our own XY tables. So it was to the 4th degree, and now our polynomial is reduced to the 3rd degree. And what it's actually producing is a 4-term polynomial, where if we're looking for zeros, one of the methods is factoring. And one of the methods that we had learned previously was grouping. So we're just going to group them the way they look. Pull out what they have in common. So my first pair pulls out an x squared, leaving me with 2x minus 3. My second couple, they also have in common a 4, so I'm going to pull out a 4, leaving me with, again, 2x minus 3. Notice that these factors are the same, so I can take what they had pulled out, create a factor amongst the two of them, and then, ta-da, I have reduced that factorization. So when actually zoning in on what are the zeros of the polynomial, okay, we've already identified 5 is a 0. So now we must set our new factors equal to 0 to figure out what their specific roots are. So over here I'm going to add 3 and divide by 2, giving me a root of 3 halves. Over here I'm going to subtract 4 from both sides, and then I'm taking the square root essentially in a moment here of -4, which I guess your imaginary number alarm should be ringing off the hook. So x is going to be equal to, when we take the square root, we get a plus or a minus. The square root of -4, that's going to produce a 2i, and we have now identified 2 complex roots and 2 real rational roots.